In today's class, we are going to discuss about magnetic scalar and magnetic vector potential. As we know, in magnetic field, there are two types of potential. One is scalar magnetic potential, which is denoted by Vm, and the other one is vector magnetic potential, which is denoted by A bar. In order to define the scalar and magnetic vector potential, we are making use of two mathematical vector identities. First identity is del cross del dot V is equal to 0, where V represents the scalar quantity, and the second vector identity is del dot del cross A vector is equal to 0, where A vector represents the vector. First, we are going to discuss about scalar magnetic potential. If Vm is the scalar magnetic potential, then it should satisfy the equation number 1, that is first identity del cross del dot V is equal to 0, where V is a scalar quantity. So when we just substitute, what we are doing is we are replacing the scalar magnetic potential by V. So therefore we get equation 1 changes as del cross del dot Vm is equal to 0. Keep this equation as number 3. Next, we know that the relation between magnetic field intensity and magnetic scalar potential is given by H is equal to minus del dot Vm. Keep this equation as number 4. Now what we are going to do is, now we are just going to substitute the equation number 4 in equation number 3. That is, instead of in equation 3, instead of del dot Vm, we are just replacing that by H. Since that del dot Vm, it is here, H is equal to minus del dot Vm, then when we substitute there, it becomes del cross of open bracket minus H close bracket is equal to 0. So that is that can be written as del cross H is equal to 0. Keep this equation as number 5. As we referred earlier, from the point form of Ohm's law, it is del cross H is equal to J, where J represents the current density. While comparing equation 5 and 6, it is clear that the value of J is equal to 0. So we also know that Vm is equal to minus H dot di. So whenever we are solving the magnetic scalar potential, it is represented that the current density value is always equal to 0. So we know that in magnetostatics, Gauss law, surface integral B dot ds is equal to 0. So taking the B magnetic flux density outside, so it is B double integral surface integral ds is equal to 0. Instead of this surface integral ds, that can be replaced by del. So therefore del dot B is equal to 0. Next, we are going to calculate the value of magnetic vector potential. We know that from the second vector identity equation, del dot del cross A vector is equal to 0, where A vector is called the magnetic vector potential. We know that del dot B is equal to 0, as referred earlier. Keep that equation as number 7. From magnetostatic Gauss law, so we are just going to compare the above two equations, that is equation 6 and 7. We get del cross B is equal to 0. We also know the del cross A, right? B is equal to del cross A. So from the above equation number 8, that is B is equal to del cross A, the curl of magnetic scalar potential is equal to the magnetic flux density. So this is the relation between magnetic vector potential and magnetic flux density. So we know that the point form of Ohm's law, which is given by del cross H is equal to J. So from which we know that H is equal to B divided by mu naught. Instead of H in the first equation, I am replacing that by B by mu naught, and therefore del cross B by mu naught is equal to J. So in electrostatics, we have already discussed del dot D is equal to rho V. Similarly here, it is del cross B is equal to mu naught into J. Keep this equation as number 9. We know that from equation number 8, B is equal to del cross A. So we are just substituting that in equation number 9. We get del cross A is equal to minus mu naught J. So we know that by mathematical identity, this is one mathematical vector identity, del cross A is equal to del of del dot A minus del square A. From that equation, that can be replaced by mu naught J is equal to instead of del cross A, I can replace that by del of del dot A minus del square A. So now what I'm doing is I'm taking that mu naught to the right hand side. So equation 10 changes as J is equal to 1 by mu naught into del of del dot A minus del square A. So to solve the keep this equation as number 11. To solve the magnetic scalar potential, the current density is always 0, that we know that. And whereas for solving magnetic vector potential, the current density value is not equal to 0. It depends upon the magnetic vector potential. Next, what we are going to discuss is we are going to discuss about force between two differential current element. So force between two differential current elements. What we are going to do is we are going to consider two current elements with two current in the same direction. Let the current be on the element I1B I1 dl1 and the current element of 2B I2 dl2. So now we have current element 1 and current element 2. So the current flows in both the element, it is in the same direction. Now you could say that from the above figure, the current flow are in the same direction and hence both the elements experiences force of attraction. So the differential force equation is given by d of df1, which is equal to that is the differential current element 1 I1 dl1 into the differential magnetic flux density on the current element 2 db2. We know that by Biot-Savart's law, dH is equal to IDL sin theta divided by 4 pi r square into Ax vector. So therefore db2 is equal to minus mu into dh2. So sorry, dp2 is equal to mu into dh2. So therefore dh2 is equal to I2 dl2 sin 90 divided by 4 pi r2 square, which is equal to I2 dl2 sin 90 value is 1 divided by 4 pi r21 square. So that can be replaced. That can be written written as db2 is equal to just multiplying the value of mu naught into I2 dl2 divided by 4 pi r2 square into ar. Now we are going to substitute the value of db2 in equation number 1. When we substitute the value of db2, we get d of df1 is equal to I1 dl1. Instead of db2, I am writing mu naught I2 dl2 divided by 4 pi r21 square into ar21. Therefore, d of df1 is equal to mu naught I1 dl1 into I2 dl2 into ar21 vector divided by 4 pi r21 square. Now we have d of df1. Our aim is to find out what is the force between two differential current elements. For that, we are just going to integrate the above equation twice in order to get the value of force. So therefore, we are taking the constant outside. F is equal to F1 is equal to mu naught I1 I2 divided by 4 pi integration line integral L1 line integral L2 dl1 dl2 into ar21 divided by r21 square. So similarly, you can write the equation for force on the second element, which is given by just interchanging the subscripts. We get F2 vector is equal to mu naught I2 I1 divided by 4 pi line integral L2 line integral L1 dl2 dl1 into ar12 divided by r12 square. Now we can say that from the above two equations, F2 is equal to minus F1. This is nothing but the equation representing the concept of Newton's third law. For every action there is equal and opposite reaction. That is F2 is equal to minus F1. Now next, same concept is being applied for force between two parallel conductors. So the same condition with the help of conductors we are saying with the distance that those two conductors are separated by a distance d and they are placed parallel to each other. When therefore there exists a force due to the interaction of two fluxes. The force between two parallel current carrying conductors depends on the direction of the current. That is very important. The direction of both the currents are same, then the conductor experiences a force of attraction. If both the conductors are in the opposite direction, then the conductor experiences a force of repulsion. So this conductor is placed across the length L and distance d. Assuming the current carrying conductor is in the opposite direction, and therefore we can write F1 is equal to I1 into L into B2. Instead of this IL, I can write I1 into L into sin 90 into B2. Sin 90 value is 1, and therefore F1 is equal to I1L into V2. We know that from Ampere circuit the H vector due to the long straight conductor, this we have already found out, H is equal to I divided by 2 pi d. If it is for H2, then it is H2 is equal to I2 divided by 2 pi d. B2 is equal to mu into H2. We know the value of H2, and just in order to find out B2, just multiply the above H2 value with mu naught. We get mu naught into I2 divided by 2 pi d. We are going to substitute the value of B2 in F1. F1 is equal to I1L into mu naught into I2 into divided by 2 pi d. That is F1 is equal to mu naught. Rearranging the equation, we get F1 is equal to mu naught into I1 into I2 into L into divided by 2 pi d. Similarly, you can write the equation for F2, which is equal to mu naught into I1 into I2 into L divided by 2 pi d. So this is about the concept of force between two parallel conductors. This is also the same concept as we discussed in the previous topic. That's it. Thank you.